Okay, the average value of a function. It's basically a formula, and we're looking at an average value function of a function from A to B is actually simply the integral of the function from A to B over the fraction b minus a. So what is useful about this information? Let's take a look at a graph here. So if I look at a function, let's say a function that does something like this, and between any 2 points in time, A, and we'll go further out, B. Well, clearly, the lowest the function has ever been could be expressed by this line here, which would be the absolute min of the function. And then for this particular graph from A to B, the absolute max would be at this endpoint, always at a critical point or an endpoint. So this is the absolute max of the function. And that function has maintained values in between that absolute min and absolute max for the full time, but at what value? Now, I can really just look at this graph and give you a reasonable estimate that if this is my min and this is my max, that my average value of this function lay probably fairly close to somewhere in the middle, plus or minus, and this would be considered the average value of the function, more or less. Now, what you should notice is that if I look at the area of the object that I just drew there, that it should be the same as the area under the curve of the function. One is curved, one is a rectangle, but if they have the same area, and they need to, then, of course, what is the area of this rectangle? Well, the area of this rectangle would be its height, and the height is called its average value, times its width. Its width is b minus a, and that should be the area of that rectangle. And if it's the same as the area under the curve of the function, the area under the curve of the function, or between the x-axis and the function, is given in calculus by this function. So we have equivalence here. If I want to find the average value of my function, all I have to do is divide by this or multiply by 1 over it. And I end up with the average value of the function. So that's the explanation of it from a geometric standpoint. But pretty much it's a very, very simple formula. So let's use an example. Let's say I have a house, and the value of that house, we'll call this the price of the house, can be expressed as an exponential function. Let's say you purchased this house for $200,000 today, and it's growing exponentially by 3% continuous growth rate per year. And I'd like to know what this house value is going to be on average for the next 10 years. Okay, so what is going to be the average value of this home that you just bought over the next 10 years? So the average value of my price is going to equal, over 10 years, 10 minus 0 of the integral from 0 to 10 of my function. And basically, you just have to know how to set up that simple integral and divide. So the antiderivative of this, I'm going to move this 200 out front actually first before I go anywhere. And 200 divided by 10 is 20. And now I'll take my antiderivative. The antiderivative of E is E divided by R from 0 to 10. So let's see, we've got 20. Actually, I can take now this 0.03 out and just plug in e to the 0.03 times 10 minus, plug in that is 1, and throw it in my calculator. Any calculator will work. So what do we have here? Come on, calculator, turn on. There we go. 20 divided by 0.03 times, oops, times, parentheses, e to the, what is that, 0.3, because I'm multiplying by 10, 0.3, 0.3 minus 1. And final answer, 233. We'll round there for this particular problem. So, I had a house purchased at $200,000, expecting it to grow at a rate of 3% continuous per year for 10 years. We'll have an average value of $233,000 over that 10-year period. So it's really a pretty straightforward, simple setup.